This lesson looks at absolute value linear inequalities. So you're going to have to remember to first isolate the absolute value, then split it into a system of inequalities, and then graph each solution set on the graph. So that's what we're going to look at. Let's just remind ourselves what we do to split an absolute value inequality into a system of inequalities. So first recall, consider an absolute value of, say, let's just put x for now, being less than or equal to 5. And the other option would be absolute value of x, say, greater than or equal to 5. So how do we split this into our two components? Every time we have an absolute value, we split it into two components. If you had an equal sign, you'd just say, well, x is either the plus version or the negative version. But in this case, absolute value is on its own, but you have to think, what are all the possibilities for x? Well, at 5 and at negative 5, those both work. Absolute value 5 is equal to 5, absolute value negative 5 is equal to 5. But we want the less than, so which other points work? So, well, if we stuck a 4 in here, absolute value of 4 would be less than 5. So 4 works. Does 6 work? No, it doesn't, because it's too big. So you can imagine that all the way down to 0 would work. But what about negative numbers? So let's say you had a negative 1. Absolute value, that is 1. Yes, it's less than 5. So basically everything in between 5 and negative 5 is game. So this was the basis of splitting the system. And you can recall that this essentially became x between negative 5 and 5. Now you can also see this as an AND statement of x being greater than or equal to negative 5 and x being less than or equal to 5. So the first one is x less than or equal to 5, and then you're pairing it and intersecting it with the negative version, but the opposite sign of that. So that's how you would split that system. Now let's recall how we would split a system that's greater than. So this is the same example, so the equal part is going to be at 5 and negative 5 again. But this time it has to be greater than. So essentially you're looking for numbers that, without their sign, are bigger than 5. So what do you think? Well, 6 works, because 6 is greater than 5. 7, 8, 9, and so on. Does 4 work? No, 4 doesn't, because it's not less than, it's greater than. So because of that greater than sign, we're splitting it into everything bigger than or equal to 5. In this case, it's equal to because of the endpoint. But then also, we can't forget that we're also having all of the numbers that are less than or equal to negative 5, because, say, for example, negative 6. Negative 6, take the absolute value of that and you get 6. So when it's greater than, we have the outskirts. So then we have x being greater than or equal to 5, or x being less than or equal to negative 5. Now we have an OR statement here because we want to have both parts be included. So this is just a reminder of how you split your absolute value equations or inequalities. So let's look at some examples. First example here only has one variable. So you'll notice you could actually use this and graph it on a single variable grid, but you could also graph it on a 2 variable grid. Depends on what is being asked for. So we'll do both in this case. So first off, because it's less than or equal to, we want to split it. But we can split it by saying that it's in between the 4 and the negative 4. So this means that we need an AND statement. So we can signify that by a set of a little curly sign here, like a bracket. So then you could say that x minus 1, which is my absolute value, and it's isolated. Make sure it's isolated, make sure there's nothing else, make sure you solve it first. So x minus 1 is greater than or equal to negative 4, and x minus 1 is less than or equal to positive 4. So essentially we've split our system. After it's isolated, we split it, and now we want to graph. And we could graph these on either, but first you might want to solve them. So this first inequality, let's add 1 to both sides. So you have x greater than or equal to negative 3. And this second one, add 1 to both sides, you have x less than or equal to 5. So what does this mean? This means that we want all the points greater than or equal to negative 3. So negative 3 is right here. Now x equals negative 3 is this whole line. It's this vertical line. But we want everything that has x values that are greater than or equal to negative 3. So that's everything on this side of the graph. And the second one tells us x less than or equal to 5. So the maximum is 5. And so everything less than that would be everything here. So you can see the common part, because of the and, because the in between, is just the in between part. So it's just in between this negative 3 line and this 5 line, x equals 5 line. If you were to do it just on an x-axis graph, you'd have between negative 3 and 5, just as you've done before. Let's take a look at another example. This one also has one variable, so it also could be a one variable example or a two variable example with the y missing. But the biggest attention should be drawn to the fact that now it's greater than. So I always draw this little picture for myself to help me split it. I know it's greater than 3. Absolute value is by itself. It's isolated. That's great. So then I say, well, it's on the outskirts. So because it's greater, it's everything that's bigger than 3. And also, which is an or statement, or less than 3. Now, the boundaries are not included, so we have to make sure to draw little dotted lines. So now this splits into, and this picture can help you split it because it'll help you decide how to write your system. So you have x plus 2 is less than negative 3, or, and now I'm looking at this other part, x plus 2 is greater than 3. So I've split it into my components, and again, now I can subtract 2 from both sides, so I have x less than negative 5, or subtract 2 from both sides, x greater than 1. So you can see that essentially our whole thing has just shifted over by 2, and you'll just see that in a sec. If we put it into the one-dimensional graph, that would be x less than negative 5, or, which means include also x greater than 1. So you can just see that this little interval has shifted. So if we want to draw this as a 2D graph, we just do the same thing. So it's less than negative 5, but not including the negative 5. And then also greater than 1, but not including the 1. So all of those points signified by this graph will satisfy this inequality. So now we've got an example with two variables, so we actually need the grid because we've got the two variables, but the splitting part is the same, and it's also already isolated, so we don't need to isolate it. So because it's less than, again, I always draw myself a graph that means it's less than 3 but greater than -3. So because it's a combination, we need an AND statement, so it's x minus y is less than 3 and x minus y is greater than -3. So now I want to graph both of these inequalities on my grid and look at the AND component, so the intersection of those two shaded areas. So to graph this, I want to isolate my y, so I could subtract x from both sides, leaving me with -y less than -x plus 3. But then I'd have to divide everything by -1. But remember, if you divide by a negative, you have to switch the inequality sign. So that's going to leave you with y greater than x minus 3. We can graph that. That's got a y-intercept of -3 for the boundary line. And so the slope is 1, so it's going up 1 over 1, up 1 over 1, up 1 over 1. And it's not including because it's not equal to, so it's a dotted line. And it's greater than. So greater than implies above, but you can check a 0 point, which would be 0 greater than -3, which is true. So everything in this top region is going to be shaded in. Let's graph the second inequality. Same thing, subtract x from both sides. So you get -y greater than -x minus 3. Again, we divide everything by a negative, just like the above example. That'll leave us with y is less than x plus 3. So we've got our x plus 3 starts at 3 and also moves with a slope of 1 over 1 and is also dotted. And because this was less than to begin with, you can kind of tell it's going to be a between type, because see, this one is less than, so you can see that 0 does work, because 0 is less than 3, so that means we shade the whole bottom of this. And since it's an AND question, we're looking at the intersection, which is just the common part, the in-between part. So again, you want to make it clear as to what your final answer is, and your final answer should just be this middle region here. Let's try one more. Now this is pretty much the same question, except we've got a greater than or equal to. So remember, the greater than is going to be the outskirts. So you can already kind of, hopefully intuitively tell that instead of it being the middle region, it's going to be the outskirt region. But let's take a look in particular. So because it's greater than, remember we split it into the greater than 2, or, so we want to include both, the x minus y being less than or equal to the -2. So that's going to leave us with solving these again. And similarly, we get to flip the sign when we divide by -1. So y is less than or equal to x minus 2, or, and we do the same thing. Now notice you could do the same thing, or you could actually add y and then add the 2, leaving you with x plus 2 on this side and then y on this side. Now you can see if you read it this direction, that actually says y greater than or equal to x plus 2. But you can prove that for yourself if you like, or do it the way that the first one was done. So let's graph these two. So y less than or equal to x minus 2. So this means we start at -2 and travel also as a slope of 1. And this time we're including the line. And it's less than, so it's the bottom component. You can try with a test point. 0 does not work. And following our intuition, we're supposed to have the other outskirt being there. So you can actually see that that does indeed work. It starts at 2 and travels at a slope of 1. And the upper region is being shaded there. You can see that 0 is not in that either. 0, 0 is not included. So there's an example. Always remember to isolate your absolute value before splitting it into your cases, and then follow all the methods as outlined before.